Welcome everyone. My name is Britt and I'm the marketing manager at Eatron Technologies. We're very excited that you're here with us today for our very next Talk to an Expert. We are going live every last Thursday of each calendar month, so please keep your agendas open. If you're not following us yet on LinkedIn, please do so that you won't miss any future live events. In case you miss one of them, you'll find them all on Spotify, YouTube, and on our website. So, for those who don't know us, Eatron is an international technology scale up dedicated to making software defined vehicles a reality for OEMs worldwide. Our house rules are if you have any questions, please put them in the chat and they'll be answered at the very end. Today's expert is Krzysztof, our BMS Product Manager, who is making a comeback. Could you please tell us a bit more about yourself for the people who haven't tuned into episode 1 yet?
Yes, thank you, Britt. Good morning, good afternoon, good evening to all of you, wherever you're checking in from. Really great to have you here, and I'm also excited to be here again, back at the hot seat. My name is Krzysztof Slosarczyk. I'm the BMS Product Manager at Eatron Technologies. My personal background is in controls engineering, and I pretty much spent most of my life, professional life, working on batteries. And just a few weeks ago, I actually celebrated a 15-year milestone. So you can gauge how old I am if that's not clear from the picture. But I've spent quite a large amount of time working for Jaguar Land Rover on various battery-related and BMS-related projects, and also worked with multiple startups doing similar sort of roles. And my sort of promise for today is to only share valuable insight to all of you tuning in. And as Britt said, let's keep this as interactive as possible. Please put the questions into the chat, and I'm really excited for the next 30 minutes with all of you.
Cool. Thank you so much. Well, let's dive straight in. Could you tell us how to design a BMS to be flexible and configurable?
Yes, that's a large topic, and probably we would not finish everything. But to provide a short answer to a long question, let's start with defining what we mean by a flexible design. And everything these days needs battery, and everything that has a battery needs a BMS. We've got electric cars, we've got mobile phones, we've got soon electric planes, and a single BMS design cannot really cover every single battery, and that's we're breaking laws of physics, but there is a degree of flexibility that can be achieved when we perhaps group set and a level of applications. And electric vehicles and batteries that are used for traction are perhaps a good enough grouping. And we've got a range of batteries that we deal with. There are batteries that operate at low voltage. There are batteries that operate at high voltage. Some of them have small capacity. Some of them have large capacity. Some of them are using lithium iron phosphate chemistry. Some of them are using NMC or NCA or LTO, whatnot. So we've got quite a large constellation of different configurations, and in order to address all of these needs, it is important for companies like Eatron understanding these needs to develop a product that best addresses these needs and develop a design that is flexible and configurable, that then actually enables the quick deployment and reapplication into the market.
Thank you. What's the alternative to a flexible and configurable design?
Nice one. So the alternative would be a highly bespoke design. So looking at every single requirement, the design would only meet those requirements and nothing more. In terms of application envelope, it would only work for as for to meet certain use cases in a certain envelope. Performance envelope. So those highly bespoke designs have their presence, and typically they are driven by the economical factors to achieve certain cost saving. And typically designs which are heavily bespoke are essentially attracted to OEMs which have large volumes at hand, where some possible investment of the development effort is actually justified to make it to use a design that is essentially very bespoke for that simple application and then refined from the cost perspective.
Thanks. What's the well, actually, now that we've defined what flexible and configurable is, can we dive into the pros and cons?
Yes. So one of the so the flexible design allows for greater reapplicability of that design, and that comes at the expense of having to put quite a lot of effort to develop a design that is flexible from outright. And for companies like Eatron developing BMSs for the automotive applications, we would have to endure far greater effort to essentially think through various scenarios as best as we can to really make sure that we have covered all possible scenarios, but also validated against those requirements and those scenarios, and really kind of put the effort sort of do the work first so that others can gain from it. Because the gain then is a much faster deployment into the market. And typically, there is some level of customization. No design is always perfect. There is some level of customization. However, when we talk about the flexibility, we really want to do the high degree of sort of work and the design that is 80-90% there, and we're talking about the customizations that could mean things like, well, it's not really fitting mechanically into the box, and the box in this case could be the battery module, or it requires, let's say, some additional sensors, or it requires some additional functionality that is needed for that specific application. But the foundation as a platform solution is there. And kind of comparing this to some of the cons, typically there is a risk of actually like over engineering it a little bit. So there is a risk that some features would be there unnecessarily there, but this then comes to a discussion whether certain features that are not a must to have needs to stay there, or whether they need to be removed. So really, in a kind of pros and cons way, the flexible designs, since they have been kind of developed and validated, are far easier to deploy, and the bespoke designs will take far longer, but possibly there will be a possible lower piece cost price at the end.
Thank you for explaining the pros and cons. Could you tell us now how to design it, starting off with hardware and then software?
Oh yes, okay. So any design really starts from a choice at the architectural level, and looking at the hardware, the most effective architecture for traction batteries, since we've got a lot of cells, a lot of modules, would be to deploy the master and slave architecture, and that on its own already inherently provide the degree of flexibility and scalability. So once the design is in place, the same design can be used for 300, 400 volts battery 800 volts battery, even higher. The limitations are mostly driven by the bandwidth on the sort of communication, the choice of communication network in between the master and the slave, and also the ability to for the master to essentially measure the voltages at the pack level at the right range and accuracy, etc., etc. From the hardware architecture perspective, it's also very important to select the since the battery management system is there to protect the battery, the user, also try to get as much out of the packs for as long as possible. The safety is very, very important, and everything really starts from being able to reliably measure voltages, temperatures, and also currents. And that analog front end that really works closely to the cells is extremely important. So the choice of ASIC that supports that, and the sort of provision for a wider, let's say, uh, a good family of ASICs that could support a various number of channels is also extremely important, because then when there are applications that are better suited with an 18-channel ASIC, if the design needs to start right from the start, it's really difficult, and the design really needs to either support a 6-cell ASIC, 12-cell ASIC, 18-cell ASIC, or whatever the portfolio of ASICs is, and that's really very important to take that into account. And on the sort of the main master controller side, the choice of microcontroller is also very important. But I'll probably come to this in a second when I speak about the software. And from the software perspective, the choice of right architecture is as equally important, and typically choosing the state-of-the-art architectures like AutoSAR already provides that level of flexibility and configurability. Since the architecture is a layered architecture, it also provides some degree of flexibility to adopt the hardware elements without having to change the software too much. So putting an effort in developing the software that complies with AutoSAR architecture pays off. Yes, it's more difficult to start with, but there are from the flexibility point of view, there are far greater gains afterwards. But AutoSAR, being the architecture, also has to host the kind of intelligent part of the battery management system, which is the actual application that manages the cells, estimates state of charge, state of health, and developing the application level software also in a smart way that provides that ability to change the chemistry if needed, or scale the amount of individual state of charge algorithms that needs to run on every single cell when deploying the BMS from 400 volts pack to 800 volts pack is really important. And typically model based design allows for that type of flexibility and configurability, and this is again state of the art development that we use heavily at Eatron.
Thanks. So now that we've captured the architectural aspects, shall we dive into an overview of key design decisions to end our lovely talk?
Yes. So we covered the hardware elements, we covered the software elements. Perhaps it's important to maybe like go up the level to the system design aspects, and most importantly, the right choice of functional safety concept and cybersecurity concept will play a big part in how flexible and configurable the design is. Here, it's also very important to balance out the and make sure that the system is not over-engineered too much. For those who understand functional safety and the different ASIL levels, probably everybody would like to have an ASIL-D BMS in their batteries, in their electric vehicles, but it's very, very expensive to develop BMS that provides that level of safety assurance. And not always this is required, right? So if various OEMs through their analysis arrive with the understanding and conclusion that ASIL-C is sufficient. There is no real argument to be essentially paying extra money for an extra cost when it's not actually needed. So it's really important to design the system with the right concept level considerations to do it at the level that is providing the biggest coverage of all the applications, but also with the clear understanding that should there be a need for upgrading the system to an ASIL-D, what would those considerations be? And from my experience, there's only like few OEMs who really kind of are going as far as ASIL-D, and most of the OEMs are happy to stay at ASIL-C. But this is a topic on its own, and but the choice of the concept is very, very important. The same really applies to cybersecurity concept. It's important to strike that right balance and not over-engineer the system, but engineer it in a way that is fit for purpose, and it's adaptable enough to then work for a given application. And perhaps just to finish the talk on the design aspects, it is also important to kind of be pragmatic and actually take into account the fact that we have the sort of chip crisis coming out of the pandemic, and some of the components, some of the design actually is driven by the practical constraint of components availability, and that also steers the design one way or another. But we're coming out of this, and hopefully we're seeing the end in the tunnel. Those kind of big ideas at the concept level can needs to be also confronted with the reality as to what components can be actually sourced in the first place.
Cool. Thank you so much. Thank you for answering all these questions. Let's look at the comments and see what everyone else would like to know. We've got some Eatronians who are asking questions whilst everyone else is typing them. So the very first question is, do you see a general trend to a strict separation of 400 volt and 800 volt vehicle architectures, or also growing demand for architectures with dynamic switching between the two high voltage levels, which needs to be covered by BMS design?
Yeah, really good question. Honestly, I think the trend isn't that clear yet. There is a lot of really good work. I mean, Porsche Taycan is one of the I think most complex EVs out there, where we've seen different sort of voltages, and really the kind of the push for higher voltage architectures are the fast charging, and I think the overall trend is there to enable that, but there is a lot of practical considerations with the charging infrastructure and being able to provide that to EV users in general. But whether it would settle down as a 800 volts only, or whether there's going to be dynamic switching between the 2 voltage levels. Um, I don't see the clear pattern yet. I see both solutions very possible, but of course with the dynamic switching, the design is a bit more complex. But both are very interesting and attractive.
Thank you. Well, I hope that answers your question. Brian is saying, really interesting talk as usual, Krzysztof. Can the hardware be designed to be configurable?
I'm a strong believer that it can be designed to be in a way that is configurable, and the configurability probably would be limited in the functionality that is not core. So if there was a need for additional, for example, CAN transceiver or an additional pyrofuse or an ability to support a certain sensor, or add more sensors, from the hardware perspective, on the way the circuit is designed, it is also designed in a kind of modular fashion. So from the design perspective, there is a greater efficiency to simply take those modules and replicate them, and that's the kind of use case for adding features on above the core. And the core consists of microcontroller, the safety power management IC, the communication to the vehicle, to the MCUs, the ASIC. So that's what I mean by core. In terms of configurability to come down, I also see that there is it's a valid use case that is achievable at the hardware level, and subject to let's say no need for changing the physical size and shape of the PCB. The design can essentially have some of the ICs simply not populated, or some of the components not populated, so they'll just stay on as trucks, but simply at the sort of, and this would help reducing the cost a lot. And yeah, the software would need to be configured accordingly, but it is possible. And the modularity to add features would be essentially on none of the core on non-core aspects, and the same applies to when it comes to essentially taking stuff out. The core needs to stay the same.
Hope it answered your question, Brian. Alexander is saying, great info. Do you think the same need for flexibility / configurability applies to low voltage BMS for 12 voltage or 48 voltage batteries as well, or is this market too cost sensitive?
I see that the low voltage BMS market is cost sensitive, because when it comes to comparing the cost of BMS for a let's say 100 kilowatt hour battery that has hundreds or thousands of cells, the sheer cost of cells overwhelms the cost of non-cells in the pack. So overall cost pack distribution, the electronics is a factor, but it's kind of far disproportionate to the size, to the cost of the cells in the pack. If we now go to the 12 volt, where we have 4 cells, and those cells are quite affordable, and typically they are made out of lithium iron phosphate cells. Those the cost of BMS can either match the cost of the cells, or it needs to be balanced out. So that is becoming far more cost sensitive, which kind of drives the need for bespoke designs. And the bespoke design the bespoke designs are particularly attractive for high volume applications. And when it comes to 12-volt batteries that are probably going to be deployed for every car has to have a 12-volt battery. The batteries are going to be designed to on its own to work with various vehicles and vehicle sort of car lines, but the BMS itself would need to be designed to be bespoke because it's going to be high volume. It needs to be designed and well cost optimized.
Cool. Thank you. Well, Alexander, I hope that answers your question. These seem to be all the questions for today. Oh, sorry, never mind. There is a question that just popped up. Iman is saying, interesting talk. Please explain your solution for SOX estimation for such battery packs that use both NMC and LFP cells types together in a pack. For example, Neo battery pack.
Yeah, the Neo battery pack is very interesting, and certainly that solution is both novel and innovative. For the SOX solution, our approach is to focus at the cell only, and the SOX solution covers different chemistries only. So we have a single solution for single chemistries. When it comes to deploying those solutions to a pack, we are not too involved yet at dealing with multiple chemistries. But I think what Neo has demonstrated is very, very interesting because it really helps with overcoming the low temperature issues on one hand, and also the state of charge estimation of the flat regions of the LFP. So the solution is very, very attractive. However, at Eatron, we have a different approach for dealing with the estimations at low temperatures and also in the flat region. And for LFP chemistries, we essentially use physics-based models for that. That's our predominantly primary approach, followed by very, very detailed and extensive characterization, and that yields very, very good results already. There is no need for having the two chemistries kind of working alongside each other to resolve the state of charge accuracy issues. Of course, Neo deployed that also for the low temperature performance issues, but but that's a pack consideration. But from the BMS perspective, our approach is to kind of really nail it down at the individual chemistry level through the choice of physics-based models and a really, really good understanding of how it all works together.
Thanks, Krzysztof. There's one more question that just came in. Dr. Gregor is saying, how much the functional safety requirements drive the cost of high voltage and low voltage BMS solutions, and what kind of factor we talk when jumping from ASIL B and D, for example?
Mm-hmm. Yes, good. Yeah, good. Very good question. Perhaps starting from the distinction between the two applications, the high voltage batteries or BMSs for high voltage batteries, traction batteries, and low voltage BMSs for low voltage, let's say 12-volt batteries. The main distinction is that the high voltage battery, when at fault, can open itself and the vehicle essentially rolls to a safe stop. The 12-volt batteries made out of lithium-ion chemistry, especially with the ADAS features becoming more and more critical for the 12-volt power to be made available and to stay available throughout essentially the drive cycle. Those are becoming safety critical devices, and if those batteries are used that way, they need to provide reliable power source, even at expense of some long-term degradation or damage. And that's the kind of key distinction that we are seeing. And when it comes to jumping from B to D, it all comes from hardware that needs to essentially be able to support those essentially those requirements. The choice of the composition to essentially make the implementation viable, and then the both at the sort of hardware level and software level, and then very solid validation that is far greater than at D than it is at B.
Thanks. Well, we've reached the end of our talk. If you have more questions, pop them in the chat, and then we'll get back to you just via LinkedIn. If you've missed any parts of this, it will be up on our LinkedIn page. Thank you everyone for joining, and thank you for the people who have put in a question, and we will hopefully see you in the next one. Bye.
Thanks everybody. Cheers.
Bye.
Thanks, Britt. Bye.
Thank you.